Imagine standing beneath a Boeing 747 as it passes overhead. You're looking at a structure that weighs 412 tons when empty. Add fuel, cargo, and passengers, and you're staring at 500,000 kilograms suspended in the air. The question is simple, direct, unavoidable. How is this not falling? We understand gravity. We feel it every moment. Objects heavier than air should descend. And yet, this massive structure climbs into the sky and stays there for 15 hours straight. This is not magic. It is not defiance of physics. This is engineering. When most people think about flight, they reach for the most obvious explanation. The wings push air downward, and by Newton's third law, the air pushes back. Lift. This is not wrong, but it is incomplete. Here is the simple version. A wing is curved. Air flows over it. The shape forces air downward. Downward moving air creates upward force. Plane goes up. Plane stays up. This explanation works as far as it goes. It is taught in elementary schools. It appears in popular science videos. It is mechanically correct at the highest level of abstraction. But that's not the full story. The real question is not whether wings can generate lift. Wings obviously can. The question is more specific, more demanding, and more revealing about how engineering actually works. What determines how much lift a wing can generate? And more importantly, what prevents a wing from generating unlimited lift? This is where the simple narrative collapses. If wings simply pushed air downward, then a larger wing should always generate more lift. But aircraft design does not work this way. You cannot take a wing and make it 3 times bigger and expect 3 times more lift. The relationship is far more constrained. You also cannot design a plane by only thinking about aerodynamic forces. A wing that generates 2.5 million pounds of force, enough to lift a 747, is subject to stresses that would tear it apart if the structure beneath that airfoil were not engineered with extreme precision. The real answer to why doesn't a plane fall requires understanding 3 interconnected systems. 1. How lift is actually generated at scale. 2. The structural limits of materials under force. 3. The balance between weight, force, and design constraints. These systems do not exist independently. They are bound together. Change one, and the others must compensate. Let's start at the fundamental level. What creates lift? The classical explanation, air pushed downward, reaction force upward, is a consequence, not a cause. The actual mechanism is pressure. When air flows over a curved surface, its behavior changes. This is not subjective, it is measurable. On the upper surface of a wing, air moves faster than it does on the lower surface. This difference in speed creates a difference in pressure. Fast-moving air is lower pressure. Slow-moving air is higher pressure. So beneath the wing, pressure pushes upward more forcefully than the pressure pushing downward from above. The result, a net upward force. This force is lift. This principle, discovered by Daniel Bernoulli and later explained through Newton's equations, is not debatable. It is physical law. But here is where engineering enters. The amount of lift depends on 3 specific variables. First variable, wing area. A larger wing surface creates more pressure difference. More surface means more total force. This is direct and proportional. Double the wing area, double the lift generation. Second variable, airspeed. This is not linear. Lift depends on the square of speed. If you double your speed, you generate 4 times as much lift. This relationship is crucial. It explains why planes must accelerate down a runway before leaving the ground. It also explains why slowing too much in descent or approach becomes dangerous. Below a certain speed threshold, aerodynamic force drops below weight and the plane descends. Third variable, angle of attack. This is the angle between the wing surface and the oncoming air. Increase it and you increase the pressure difference up to a point, but there is a limit. Beyond a certain angle, the smooth flow of air over the wing breaks down. The pressure difference collapses. The wing loses lift catastrophically. This is called a stall. So lift generation is not unlimited. It is constrained by these 3 variables. An aircraft designer cannot simply build a larger wing to carry more weight. That wing must operate at speeds and angles that remain within safe boundaries. A 500-ton plane does not stay in the air through lift alone. It stays in the air because its weight is distributed, balanced, and supported in a very particular way. First, understanding the balance. The plane has a center of gravity, an imaginary point where all weight can be considered to concentrate. For the plane to fly stably, this center must be located within a specific range along the fuselage. Too far forward, and the nose dips uncontrollably. Too far back, and the tail becomes unstable. The designers achieve this balance through careful placement of mass. Engines are heavy. They mount near the wings, not at the nose. Fuel tanks are distributed across wings and center fuselage. Cargo is loaded in sequence and position, dictated by weight distribution tables. This is not abstract theory. Commercial pilots carry weight and balance calculations before every flight. The numbers determine whether takeoff is even possible. Second, understanding lift distribution. The wings do not generate uniform lift along their entire span. The lift is stronger near the root, where the wing attaches to the fuselage, and weaker toward the tip. This creates a pressure environment that changes constantly from root to tip. The structure must account for this. The wing is not a solid beam. It is a carefully engineered skeleton, a main spar, the load-bearing beam, skin panels that help distribute load, ribs that prevent buckling, and stringers that add strength without excessive weight. Every component serves a purpose. Remove any of them, and the wing fails. This is where the engineering becomes visible. It is where steel and aluminum and composite materials meet the physics of force and deformation. When a 747 takes off, the lift forces it must generate are enormous. Imagine pressing upward on a fuselage with a force exceeding 2.5 million pounds. The structure experiences stress. Stress is force divided by area. A wing root, the point where maximum bending occurs, must resist this concentrated load. The designers achieve this through material selection and geometry. Modern aircraft use aluminum alloys. These materials have a yield strength, a point beyond which permanent deformation occurs. Engineers design the structure so that under maximum flight loads, stress remains below yield strength with a safety margin. But that's not the full story. When the wing is loaded upward by lift and downward by its own weight plus fuel, it bends. This bending is not invisible. On large aircraft, you can see it. The wing tips deflect vertically by several feet during normal flight. This deflection is not damage. It is designed behavior. The reason, as the wing bends, the shape changes. This change reduces stress concentration at critical points. It is a form of passive load distribution. The structure shares the burden more evenly. But there is a limit. Bend the wing too much, and you approach the buckling point, where the thin skin panels that make up the wing surface begin to wrinkle and collapse. This is catastrophic. Buckling leads to sudden structural failure, so the design must balance conflicting requirements. The wing must be rigid enough to prevent buckling. It must be flexible enough to distribute loads across its structure. It must be light enough that the lift-to-weight ratio remains feasible. This is not a simple calculation. It requires iterative analysis. Computer models simulate stress, strain, deflection, and failure modes. Physical tests confirm the models. Every major component is tested to destruction to prove the design margins. The reason the plane does not fall is not any single principle. It is the integration of all these principles into a coherent system. The wings generate lift because of aerodynamic pressure distribution, but that lift must be distributed to the fuselage and landing gear without exceeding structural limits. So engineers design wing attachment points and internal structure specifically for this task. The plane's weight must be balanced for stable flight, but weight distribution affects the center of pressure, the point where aerodynamic forces concentrate. These two centers, weight and pressure, must align within precise margins. If they diverge, the plane becomes unstable or uncontrollable. The materials must be strong enough to handle peak loads, but they also expand and contract with temperature. At 35,000 feet, the outer skin is exposed to temperatures below -50 degrees Celsius. At ground level in summer, it might exceed 60 degrees Celsius. The structure must accommodate this thermal expansion without creating stress concentrations that fail. But that's not the full story. Consider fuel. A 747 carries over 200,000 liters of jet fuel. This fuel provides the obvious benefit. It powers the engines, but it also serves a structural purpose. The fuel is carried in tanks within the wings. This distributed weight lowers the center of gravity. It also provides mass that damps oscillations, the natural vibration modes of the structure. As fuel burns during flight, weight decreases. This changes the center of gravity, requires adjustment of control surfaces, and reduces the buffering effect of fuel mass on vibration. The flight management system accounts for this. Fuel is burned from specific tanks in a specific sequence to maintain balance throughout the flight. This level of integration extends to the control systems. The plane does not maintain steady flight by the wing structure alone. Active control surfaces, ailerons, elevators, rudder, constantly adjust. Hydraulic systems powered by engines drive these surfaces. Pilots or autopilot systems command these movements based on continuous measurement of pitch, roll, and yaw. If any system in this chain fails, if sensors fail, if hydraulics fail, if control surfaces jam, the plane does not simply fall, it becomes uncontrollable. The pilot's training and the aircraft's design include redundancy, multiple hydraulic systems, multiple sensor suites, multiple pathways for control. So far, we have discussed the plane as a stable structure in calm air, but the atmosphere is not calm. Wind shear, turbulence, vertical currents, pressure variations. The plane encounters all of these. When the plane enters a downdraft, air moving downward, the effective airspeed decreases relative to the air mass. Less relative speed means less lift. If the downdraft is strong enough and the plane is flying slowly, during landing approach for instance, lift can drop below weight. The plane descends. This is not structural failure. This is physics. The solution is to maintain sufficient margin between actual speed and the stall speed. This margin is called safety margin. It is not negotiable. Turbulence creates rapid changes in angle of attack as the wing encounters vertical air currents. This causes the wing to bend and flex rapidly. The structure must absorb this cyclic loading without fatigue failure. Fatigue is insidious. A load applied once might cause no permanent damage. A load applied thousands of times causes microscopic crack growth. Eventually, cracks propagate to critical size, and failure occurs. Aircraft undergo rigorous fatigue analysis. Engineers estimate how many flight cycles, takeoff to landing, the structure must withstand, often 60,000 cycles or more. They then test materials and designs under repeated loading. A wing skin panel might be subjected to millions of load cycles in testing to prove it can survive service life. But that's not the full story. Age matters. As aircraft accumulate flight hours, the material properties change. Aluminum becomes more brittle. Fasteners loosen. Corrosion initiates in hidden crevices. Eventually, every aircraft reaches an age where continued operation becomes unsafe. This is why commercial aircraft are retired after 25 to 30 years of service. Typically, their structure is not suddenly dangerous, but the safety margin, the buffer between normal stress and failure, has eroded. The economics of maintenance no longer justify continued operation. Now we arrive at the real answer to the question, why doesn't a 500-ton plane fall? The answer is not that the wings are magical. It is that the entire aircraft is an optimized system operating within constraints. Engineers face competing demands. Make the structure lighter, and it becomes less able to withstand peak loads. Make it stronger, and weight increases, requiring more lift, requiring more speed, requiring more fuel. The optimal design minimizes weight while ensuring strength, durability, and safety. This optimization is not theoretical. It is relentless and specific. The thickness of wing skin panels is calculated to millimeters. Reduce thickness, and buckling risk increases. The spacing of stringers that reinforce the fuselage is optimized. Too close, and you add unnecessary weight. Too far, and buckling occurs. The size of hydraulic lines, the placement of weight, the geometry of attachment points, all are optimized. This optimization means there is very little margin for surprise. A 500-ton aircraft operates close to its designed limits. This is not negligence. This is the only way to build an aircraft that is economical to operate. The safety margin is built in through conservative design factors and rigorous testing, not through oversizing every component. The reason a plane doesn't fall is that it was never designed to fall. Its structure, its aerodynamics, its control systems, and its operational procedures are all integrated to prevent falling. This integration is the achievement. So the next time you see a massive aircraft overhead, you are not witnessing a violation of physics. You are witnessing the application of physics at scale. Hundreds of engineers spent years optimizing every component. Materials, scientists selected alloys with specific strength-to-weight ratios. Aerodynamicists shaped the fuselage to minimize drag while maintaining structural integrity. Systems engineers created redundancies to handle failures. Test pilots validated the design through flight testing. The plane does not fall because it cannot fall, not without catastrophic failure of multiple independent systems. But this raises a new question. What happens when those systems are pushed to their limits? What are the failure modes of modern aircraft? And how do design engineers prevent them? That is another story entirely.